with 80% times.
So it's not a bad case of deja vu you're having on the schedule again. It will be less than what Jenna talked about, mainly for the reason that this is brand new stuff. And we haven't even processed the full data set with this, so this is just all emerging. Now, if you have a faint recollection of my previous talk, I had this schema with image processing and diffraction processing, and now, since we are focusing in the EU on this, we are also focusing on this, and this is the most mature part, so I just want to spend a few words now on this. Notice that the circle does not extend around phasing. Now, this detailed processing scheme is, I think, similar and different to what we heard how MRC does it. So I have several slides that explain this in much more detail, so I just want to go through the steps. So you have a search and extract where you detect and refine the lattice and extract the reflection data from all the predicted lattice positions. Then we need to find the index origin, because as you see before, the CCD beam sort is just somewhere. It's not a Fourier transform of an image, so you don't know where it is. You need to find it.
Are you talking about image?
About diffraction processing. Okay. Then we calculate the tilt from the lattice and thereby can assign Z star and the resolution to all the reflections. There's the step to symmetrize the data set, to scale the amplitudes to some sort of reference. Polymorphic here meaning that the reference can be another image, a set of merged images, or potentially a 3D data set or a 3D map that you already have. And of course merge it all together, and the discretization step, we go from Z star to L. With the added complication, as was also mentioned, that there's not really a proper procedure to do that. Messy, the zinc function fitting and stuff. Now here's the even more detailed version of that. And I put this up for the following reason. We had a question in the last session about how IPLT is used. There's all a set of image processing routines and classes. And this is now a perfect example how we use it to implement processing. And what you should see is a continuous flow with various colored boxes. Now yellow denotes something in Python. So you see this if SE box, and so all the big boxes that I just explained, just Python scripts. Now there is blue algorithms, so algorithm objects written in C++. Occasionally there will be one written in Python because it's fast enough to do it in Python. And in green we have these basic types. Now in a procedural language like C or Fortran, you just have integers and floats. But in an object-oriented language, you make your own types to have perfect encapsulation. And this is why I want to differentiate between something that does applies a certain algorithm, which is a storage facility with a more or less sophisticated interface. Now, the in-between results here are, while you start with an image, always a reflection list. And the reflection lists vary a little bit. You have different kind of information. So the Z star is added here, and here you also go from intensity to amplitude, and here you get rid of the Z star and have the discretized L spacing. So this is really the combination of Python and C algorithms and classes that we envisioned in the beginning and that has been put to use here. Let's see. The first step, to search and extract the lattice. This is what I'm showing you is all automated. I have 2 points, I forgot to mention this. Here and here, you're required to add data from the project XML file. So we have one XML file that describes everything you might want to describe, and the data is right in here. You're required to add the spatial unit cell. Here, you're required to add the particular symmetry. And of course, the scaling doesn't work without a reference. But other than that, it's basically you start with a single TIFF file and the thing just runs through. So do a peak search. on the image. And then we do something we call a difference vector image. So between all the peaks you found, you take the difference vector, and then you plot the position or the value of the difference vector in a new image. And just accumulate that. And finally, this looks like this. And then you know where your origin is. You just take the two closest peaks. You do another peak search on that. You take the two closest peaks that follow a certain convention. So the angle has to be smaller than 90 degrees, I think, for reciprocal space in the convention, and the smallest vector is A, and the second largest is B, and stuff like that. And that's your first lattice estimation. You even use a 2D Gaussian profile on each of these peaks to really get the fractional pixel coordinates for your initial lattice. Because obviously if you have the A vector wrong in a small fraction at the 2020 reflection, this will really sum up. So it's important to get this location rather precise. Then you run a prediction for all lattice points. So you know how large your diffraction pattern is, you know where your lattice is, so you just fill everything with there. Should be a profile, a reflection sitting. Each of these is fitted with a 2D Gaussian profile. So this is really zero knowledge. You go to a point in the image, say, this 21 by 21 pixels, that should be a peak. Let's see if we can find one. And that's the reason why this particular step is the longest. It takes about 8 to 10 minutes on a fairly modern Linux single processor workstation.
Does this work if you have two crystals overlaid? Or does this only work for single crystal diffraction patterns?
That depends what happens here. So we have a pathological case where we really have two lattices that have the same strength. There it doesn't work. Because here you might get a mixture of anything. You might find the two closest vectors that are in fact the real A vectors, and then the program uses that. So it could work or it could not work.
So do you have a chance to actually then go in manually and say, this and these are two, and this is the spot for this, and then...
Absolutely. In the demonstration afterwards, I will show that each of these steps has like a mode where you go in, you look at the stuff, and if you don't like it, graphically you just shift it around, say this is the new lattice. And then
because this was my next question, if you have a screw axis and you're missing 0, 1, then you miss the spot.
Yes, exactly.
So
no, you don't. You don't, because the peak search picks out all reflections, and since you're doing all the difference vectors in a missing reflection that only along the, I don't know, H0 and 0K line, but all the remaining reflections are there, so you actually have the 1, 0 and the 0, 1 difference vectors somewhere, which have added up. So this is no problem. And that's in fact the power of this algorithm, that you really look at all the reflections that are there. And you also don't have, this peak search, you will find peaks that have nothing to do with the lattice. And since they only appear once or twice, it's just average out. So once we have this 2D Gaussian profile, which you see down here, this is a 9-parameter Gaussian profile. Why 9 parameters? The amplitude is 1. The position of the peak is 2 and 3. The width of the ellipsis is 4 and 5. The angle is 6. The height, the absolute height, is 7. And we have a background backplane tilt, which is 8 and 9. So we fit 9 Gaussian parameters. And only the amplitude and the half width need a fairly acceptable estimate to begin with. The rest will be fitted without problem. So to refine the lattice, now obviously half of the points that are predicted will have noise or nothing. So we have a filter mechanism which kicks out those, for the fitting, kicks out those. So this is rather stringent criteria. And then for the positions we have, which are again sub-pixel, because the Gaussian is somewhere, not necessarily in pixel borders, we can do a least squares refinement of the lattice. In our experience, this is fully sufficient. So we have a really well-defined lattice after that. And then we filter the profiles based on more relaxed conditions and do a box integration of those that meet the criteria. And it's a growable box. So you start with a fairly small profile, and the outer ring is the background, and you just increase it by 1 step until the background doesn't change anymore. So you really change the profile. It's a square profile nevertheless, but for each single reflection spot on each image. And in the end, you have an intensity and a background for that intensity.
Going back to Rich's question, if you have two, you very often have overlap of two. So does it take care of heat overlap, or they just get the leaders and say these are not good diffraction spots?
I don't know. I would guess. First of all, so it's not detected. So this may introduce problems. This growth algorithm, if the lab overlap is severe, you will never have a stable background estimation, because no matter how large you grow, you always have some part of repeat. And then this will be rejected. But it could be, of course, the case if you have sharp points and you go fairly out, that you actually see two peaks as one, because then you have a stable background and you will get one wrong signal. That would have to be investigated on a per image basis.
So that's where the strength of the program, processing, that you can start to work with these type of things. That would be very powerful if you could use these detections.
So this profile fitting is like our first implementation, and I anticipate if these problems come along, there's these pathological cases.
And not so pathological, but actually.
Well, pathological in the sense that it's very difficult to process them right now. Not pathological that you cannot use them, but just that it's difficult to process them. And then, yeah, we will see what we can do. Or maybe you will hire two smart programmers. Okay, so now I still have to stress that the origin of the lattice is just somewhere. We usually take it approximately in the middle of the image, but we have to find the origin. And then we have two heuristic algorithms to do that. So the first one is that for each reflection that meets a certain filter criteria, we know the background. So we just make a new image with all this background information, and this is what the image looks like. You see there where the beam stop would be. Now this is not reflecting the image. I mean, if the lattice was somehow tilted, you would have this rotation here. So this is the indices of the reflections that are now the pixel. And that's sort of a similar idea than in MRC, that you have a radial distribution of background, but here we're just fitting a Gaussian again. So we can have some anisotropy. That doesn't matter at all. And once you fit this here, this is what it looks like. You see there's a large batch of missing data in the middle where the beam stop is, but the signal out here is strong enough to actually fit this Gaussian. So at the position of the Gaussian center, we just say, okay, that's our origin. The second thing we do, we take...
The center is doing the lattice approach at MRC. You know, we actually index the spots and do similar indices.
It's more accurate. We tried to do the Friedel approach, and actually, yesterday I told, I think, Ken and you that we used the Friedel maze to find the origin, and I discovered today that we kicked that out because it was too unreliable. But we in fact tried to use Friedel maze to search the origin, and this works much better, because you use much more information. Now the second, what you can do is you take the mirror image of the diffraction pattern, you do a convolution, and then just find the peak, which is sort of a similar approach but works in the whole image. And please don't ask me the rationale for using this. This is one of those, late night decisions, brainstorming things with the group. And here you can see this is the peak that's taken. Now this is reflecting the actual diffraction pattern. So the beam stop would be about here, while this is again the indices, which is not related to the physical image. And I would say 90% of the origin determination, even for very difficult 60-degree data, works fine. Well, the tilt geometry, and there, Henning has escaped now for this discussion. I don't know why he needs 5 parameters. I really don't. We have 2. Maybe we're doing something wrong, or we're missing out on something. So we have the lattice, which is very precise. We use Shaw's algorithm to give us the orientation of this and the tilt angle. Now, this allows us to put the z-star values in the reflections. And if it turns out to be more complicated than we currently understand right now, it's no problem, because being an object-oriented software, we just have this class called tilt geometry that Shaw's algorithm uses. So we as a user, we don't care. We hack it in once, and if you now want to say get tilt axa, whatever it is called, somebody will code it once, just like Henning wanted, and it removes all of the headaches. And finally, we have the scaling to a reference, and this is, I think, the most sophisticated piece in here, and I'm going to try to explain it to you in a very compact way. So we're creating, in essence, conceptually, we're creating this 2D plot where we take the amplitudes of an HK pair where we have in the image, in the original diffraction image, and of the reference. And we're taking, so this one would be the image, and we plot it, amplitude is in the x-axis, and the pair in the reference has an amplitude here, so we plot it at this position in the plot. Now we have two sets of weights, which are given by the amplitude background ratio. We have one for our image, and we have one for the reference. So we have a weight in x and in y. And if you look at the standard implementations of linear fitting, they only take weight in y into account. So we grabbed the numerical recipes, implemented this xy error fitting, and now we can do a linear fitting through here that takes the weights, the different weights into account. So again, this is the philosophy. We're not chucking away any data. The data that is bad is just weighted extremely low. And the linear fit that we get here goes through 0, so we force it through the origin. That's also something that I would like to discuss. Does that make sense? Can there be a constant factor for a diffraction image, for the amplitudes, or does it make sense to force it all through 0? In our experience, if we let go of the intercept, things can go haywire, so we force it through the origin all the time. But it's one line in the code to change, and I'm very interested in the experience from the audience how to do that. So then you multiply the amplitudes and the sigmas by the scaling factor, and then you have the merge and the discretization. Now the discretization we don't have. So let me go back here. Up to here, everything works. It's fine, routinely. The merge is trivial, but the discretization we don't have, or we have a very crude zero-order approximation where in a window we just take all the values there, make a linear fit, and just take the one in the middle. And you mentioned before that the same fit is very unreliable, but that would be the next step to try.
But it's not so unreliable, it just blows up when you're underdetermined. And when you start a project, you tend to be underdetermined.
Okay, but here you start the project without having to use that. I mean, at the very end, when you have your 500 diffraction.
And the question is, when you start with some diffraction bounds, usually a 0 degree, and then you have to start to go into 3D by having one diffraction, so you completely underdetermine for all of the lattice lines.
Okay.
And
So
that's the problem to actually start the lattice
So we
line.
do not even use the lattice line at this point. There's no need to use the lattice line until the very end when you do the final merge. Because the scaling step here does not require a lattice line.
Yeah, but in the end you have to create the lattice line.
Yes.
And so the question is how you do that one.
Well, in the final merge, you will have the diffraction data from all images in one merge, and that's when you have to do the discretization. Prior to that, it is not necessary. So when you say the same fitting is reliable, when you have that amount of data, then I think we will proceed to that immediately to implement. Now, as I promised you before, this is the same table you've seen, but now with highlighted in black all the algorithms and the classes we use for the diffraction process from IPLT. And you can see it's a fairly complete, maybe 50 or 60% coverage. And again, this goes to the top-down, bottom-up approach that we have a need for a lattice search, and we code it because we need it in the diffraction processing. But this lattice search doesn't know anything about diffraction pattern. It gets an image and it searches a lattice, and it doesn't care where it comes from. Or the peak integration takes a little image and just integrates a peak. So I think implementing this for any image processing procedure is straightforward. You just plug in the Fourier transform of the image, tweak things maybe a little bit, but in essence you can use exactly the same.
So will you make it available that you can actually merge different diffraction patterns with different resolutions? Because not every diffraction pattern actually goes for that.
Yeah, so that's an issue that was started yesterday in the discussion, and I have to admit, we are the ones that have a bad Gaussian profile. we do not include. So we don't do it like the X-ray guys that we have a resolution cutoff, but we just have everything in the MTZ file that makes sense, and the rest that doesn't make sense isn't included. So this question does not apply. Now, if we revert that strategy and actually include the data, and we say, hey, this Gaussian profile was so bad, that means that there's almost no intensity, then we would consider the issue. I haven't even thought about that problem before, so I don't know.
And the other thing what actually people do, and the good thing to do is to throw out outliers. Once you actually do the same fit and you have the line, it's actually important to throw out the outliers because they're all very obvious ones. So
yes.
will the results still be automated or do you use by hand? Or?
Well, the goal is really to have the single image processing automated, and then say do a merge and a discretize manually or with the click of a button. I don't know. But I don't want this manual intervention. Well, the manual intervention for 10%, which are sort of with trouble. So we have a log file in the end, is, you know, this and this gave trouble, let's look at it. Or forget about it. We have 1,000 diffraction patterns.
I'm actually not talking about individual diffraction patterns, but individual diffraction scores.
Yes. Well,
so you just don't back any manual intervention.
Well, I try to go away from it because it's time consuming. But the tools we have, I mean, we have this, where is it? This plot here. I guess this should be highlighted in black also. You can plot your lattice lines in this plot viewer, and there's metadata associated with each plot. So you move with the mouse over the plot view and see exactly which image it comes from. So you have the lattice line, you have the outlier, you go there and say, oh, this is image 225, and you go and you analyze image 225, what went wrong. That's possible, but that's manual. I wouldn't know how to do that straightforwardly in an automated way. But since this is emerging, I'm not really talking about experience. There's a lot of things to do, obviously. Now, what I haven't told you is that we have what we call the ABBA problem. You can have an AB orientation, but you can just swap A and B, and, well, not swap it and move one over. But in essence, we cannot differentiate between the two. We sometimes can if we know it's 0 degree and it's a rectangular lattice, and the tilt geometry says, oh, must be 60 degrees. Then we sort of know, okay, it can't be that. But in our square unit cells, there's no way to distinguish between the two. We've tried for about 2 months to find some heuristic automatic discrimination. Couldn't do it, so now you really have to do it manually. You have to say, okay, this one is AB and this one is BA. It's very unfortunate. As I said, the discretization of the lattice line. We have coded in the symmetry, which we get from CCP4, but obviously we haven't run all the symmetry classes and all the tests that there should be. So I'm anticipating that there will be troubles with symmetries that we haven't used and that other people put in. And we can then blame the CCP4 guys because it's for their tables. And one of the reasons that I'm here, I'm very interested in this thing, obviously. What's the protocol when we're done? How do we easily go into the X-ray molecular replacement, model building, refinement? Now, we're not going to code that, obviously, but it's just sort of to establish the protocol and the procedure how to easily go that. And that's for us, which software to set up, that's to discuss with the experts here how to get that easily done. But that's also something that needs to be done for us. Okay, done as much as we can. There's a lot of stuff in the log files, but not enough yet to do proper debugging. Well, and as you will see now, since I'm done, for those that stay, the user interface is nothing as sophisticated as 2D. Nothing. It's not as painful as the classical MRC way, but it's not nearly as sophisticated. So it's mostly command line and some graphical user interface. And that was it.